Hello, this is John Pendrell speaking, and today I'd like to talk to you about some of the work we've been doing in Facies-Driven Modeling of reservoir properties. Here's an outline of the talk. We'll start off with a brief review of Bayesian inference, and then we'll talk about the Facies-Driven method, the assumptions that go into it, how we make models, how we estimate uncertainty in the general workflow, and then we'll show some examples of making models for reservoir properties and how we incorporate the ideas into Facies inversion workflows. So let's just look at Bayesian Facies analysis. And in the upper left-hand corner, you've got the familiar Bayes rule, which is the product of the likelihood ratio and prior probabilities normalized, so that sum of the probabilities is equal to 1. And on the right-hand side, we see part of the design procedure. In this particular case, we're interested in VPVS and P impedance. And the facies appear to be sandstone, gas sand, shale, and limestone. And the red blob in the middle represents a field point, say from a seismic inversion, for which we want to identify our facies. And it's a blob instead of a point because, as is indicated on those axes, the inversion is somewhat uncertain, and we should ideally account for that. And then implementing Bayes' rule, then we come up with Facies probabilities for each of the facies at each 3D cell. And the result of that is shown in the bottom right there, where we have the most probable facies. Red is gas sand in this case, yellow is wet sand, blue is limestone, and the green is shale. We tend to run this procedure on not only the field data, but also the logs, so that we can have a sort of a closed loop situation. And looking now at the inputs to our procedure, the inputs come from the Bayesian Facies analysis in the form of those Facies probabilities that I just talked about, and all facies, also Facies means. Now the means could come from the probability density functions that we used in the Facies analysis or per Facies trends. It's sort of your choice on that one. On the right-hand side, we see a couple of PDFs, one from sandstone, one from shale. The red arrow represents the field point. Standard deviation and means of those are clearly marked. In this particular case, we're looking at P impedance, say, from an inversion. And the probabilities of sandstone and shale are given relatively by the areas of the yellow and the green rectangle. You may ask, why are they rectangles instead of lines? Well, for the same reason the field point in the previous slide was a blob and not a point. The inversions have uncertainties which we have to estimate and input into the procedure. And so no matter what method you choose to get to your mean of your facies, whether it comes from these PDFs or per facies trends, the standard deviations will be giving us uncertainty information. We'll show you how we use that. First of all, some assumptions. What are the assumptions that go into this procedure? And on the bottom right there, you see typical Facies PDFs. I haven't got them labeled as to what they mean. It doesn't really matter. So the assumptions are what happens, how do I estimate reservoir properties, say, for regions between those facies, and such a point is labeled with a question mark there. It's not really under the red or the orange or any of the greens. It's kind of in between. We sort of call that a hybrid facies. And our assumption there, as shown in the first bullet, is that hybrid facies properties are represented by the weighted averages of other facies members' properties. That's an assumption. And the weights that they contribute are, in fact, their facies probabilities. And further, we assume that the property transitions between these facies members are linear. In this first implementation, we've assumed that. It doesn't really have to be that way. Maybe some further research down the line will change that. But that's the assumption here. And also, the property space is densely covered by Facies PDF. So we've done a good job of looking at all the data points from logs and wells, rock physics model simulations, whatever, to densely cover our data space with PDFs. Okay, how does it actually work? The mean properties that we've gathered from our PDFs are used to make weighted averages at particular points in property space. So if you look at the right-hand side of the cartoon there's a star in the middle, and we might want to ascertain the value of a property, be it P impedance, VPVS, or something else at that point. And we are going to take all the PDFs that we've defined for all the facies and create a weighted average for that particular point. And the weights will be, as I said, the Facies probabilities themselves. And then we've added a little calibration step so that we can tie the wells a little bit better. That's sort of an ad hoc thing that we add on at the end. In terms of uncertainties, the red areas in the PDFs shown in the cartoon are actually one standard deviation. And so we have an idea of the uncertainty in the means of our PDFs. And in the process of model building, we'll actually use this to create alternate models. So we would, at the first instance, take the mean of the PDFs to use in our weighted average to compute our reservoir properties, but we also change that mean by +1 standard deviation and -1 standard deviation, creating 3 possibilities for each facies. And if there's n facies members, that means we get 3 to the n models. So, if we had the 3 facies, that would be 27. If we had 4, it'd be 81. And then we look at the standard deviation of those set of answers and output that as an uncertainty measure, and can also, of course, output the mean model plus or minus those standard deviations if we wish. So that's how it works. Why do we want to do this? Why do we want to implement Facies-Driven Modeling? And I'm going to start calling it FDMs just for expediency there. First of all, in Facies inversion workflows, the orange boxes on the right-hand side represent inversions. They start off with initial models. They use low-frequency backgrounds, and they do their inversion thing and create reservoir properties. We can do, and the Facies part is in the green boxes, we can do Facies analysis. And you then make Facies-driven modeling models to input as low-frequency backgrounds for a further pass of inversion. We've even considered using them as initial models. It's something we'd like to try, haven't tried yet. And so the Facies becomes intimately associated with the inversion through an iterative approach, and we usually find that one iteration, sometimes 2, but usually just 1 is quite fine. I'll show you some work from that. It was already published in 2020 in the Leading Edge. As I said, we will show you that, but kind of the new stuff that I'm a little more excited about is making reservoir property models. So why would we want to do that? But just so many things we can make, and you see them listed there. Porosity for pay estimations. If we're doing pore pressure, we want, in some methods, estimates of decay, geomechanical applications. We're interested in V-quartz density, so we get Young's modulus, that sort of thing. Many applications here. And with the assumptions that I mentioned in the previous slide, there are some assumptions there. But this is really fast because the math is not all that complicated. And so for an 80% solution, this gives you some reservoir properties, estimates of porosity and water saturation, and that sort of thing, very, very quickly. Let's look at some examples now, and we're going to take our data from the Gulf of Mexico. So we have 2 vertically stacked shelf edge delta systems here, about 400 feet thick, and we're going to be looking at a small part of that. It's delta slope deformations, lump-induced turbidites, and thin-mouth bed deposits. In the seismic there, you see 6 partial stacks. We did only use the first 5. We didn't have confidence in the last, so up to 50 degrees, not enough for density here. And you see the top of the reservoir and time structure there in the upper right, and lots of faulting obviously going on. And so let's start and go through this whole procedure here. We'll start in the petrophysical domain and consider how we want to define our facies. And in my particular case, we use water saturation, effective porosity, and V clay. And defined 7 different facies members: high quality sand, low quality sand, various wet sandstones, silty, shaly sand, and shale. And you see them cross-plotted in all the ways it's possible to cross-plot them there. Those are probability density functions that were defined in our 3D space. And once that's nicely covered, we're, of course, very interested in how that shakes out in the elastic domain, because that's the domain that inversions operate in. And in terms of P impedance and VPVS here, we see that the facies shake out rather nicely. Lots of overlap, but still lots of discrimination of facies also, so we're reasonably happy with that. That allows us to go ahead and complete the facies analysis, and here we have done that. And you see the color code for all the facies on the right-hand side. The red is the high-quality sandstone, and you see that right in the upper part of the reservoir, lots of red up there, and then down deep in the bottom, in the middle, there's some more of that. Of course, it's Facies probabilities that we need in this procedure, so let's check those out. The top left is our most probable facies, but then you see for all the other facies members where they have high probability, medium probability, in fact, low probability. High quality sands again are at the top and in the middle. You see that in the bottom middle panel, where they can be confused with low quality sands too. That's part of the objective, is to be able to separate those out. So let's get into some design now to make some reservoir properties, and we're going to start with do these one at a time. I find it convenient to do 2 or 3 at a time. So we're going to look at effective porosity and density first, and we're going to see how our facies shake out in a porosity density space. And we actually have an upper layer in this reservoir and a lower layer, and things are a little bit different in each one. That's fine. We can make them different. You may be saying at this point, John, you started off about P impedance and VPVS. You defined your facies that way, and all of a sudden now we're talking porosity and density. What's the deal with that? Well, P impedance and VPVS are important because that's what the inversion creates for us across the project. And of course, we know P impedance and VPVS at the well through well curves. So now we have a connect between field space and well space. And having made that connect, and these facies are the connectors, we can now talk about other properties, and we shall do so. Having defined those PDFs, we can now make our models, and using the procedure that I've showed. And in fact, here is the effective porosity. On the right-hand side is our mean model. The wells have been overlaid, so the wells don't really, we don't tie to the wells unless I go through that little calibration step at the end. But other than that, no. So reasonably good match, I would say, at least at this scale, from the mean model to the wells. And in the bottom is the uncertainty estimate. It's a different scale, so it's about 1/10 of the scale of the upper panel. The interesting thing there is the variability of the uncertainty across the project. So it's varying with facies, and apparently the uncertainty when we have high-quality sands and low-quality sands, that sort of pay region is more uncertain than in some of the shalier regions. So interesting little result there. So I tend to refer to that as sort of like a dynamic uncertainty, if you will. Let's take a closer look and just see how good these matches really are. And we find, comparing the white is the well filtered off at 40 hertz, and the green is the same for the model. And we do find, and not unsurprisingly, that the low frequencies are a better match than the higher frequencies. Higher frequencies, yeah, there's some of the character is still there. But perhaps some of the absolute values are lacking a little bit. But that's a natural thing since we're not explicitly tying to the wells. We can look at the effect of the standard deviation uncertainty estimates. And here we're just doing a close-up look, and the green is the mean model, and then the yellow is -1 standard deviation, the red is plus a standard deviation. And so these are, given that the assumptions we make are true, these are the uncertainties that result from the procedure. And we, of course, made a whole effective porosity volume, so we just got curious and wanted to look at some slices in the upper part of the reservoir and in the middle part of the reservoir. On the left-hand side, it's all pretty porous up there, but it's sometimes wet, and the quality of the sand varies. And we can see the bright yellow is mapping of where the best porosity is, and the lower part of the reservoir, it's come and go in terms of good sands. They mix with the low quality sands also, but we are seeing some high porosities there in rather patterns that are indicative of some kind of sedimentary deposition. And if I just click, we can just take a look at a couple of other slices. There's one, another one, and another one. So we can take this glass bottom elevator tour through the reservoir, which I won't take any further here, and check out our whole volume. And now let's look at density, since we also modeled that. In the upper panel, you see the mean model with the wells overlain. In the bottom, the dynamic uncertainties. And again, not a bad match to the wells, perhaps an alternative to the inversion density when one doesn't quite have the angles to get a reliable estimate. Let's go on to estimate clay volume and water saturation. We do these together, and we see the PDF design in the upper green in the upper panel and the lower green in the lower panel. And we've truncated our PDFs here to so that the water saturation doesn't exceed 1.0 as we would expect, and that the V clay does not go below 0. And then we build our models, and here it is for water saturation with the wells overlain at the top. Hardly see them really in this picture. And the water saturation is very much near 1, except near the presence of sands as expected, and we have our uncertainties below. More uncertainties around those sands as we would expect. In modeling clay volume now, upper right is our mean model with the wells overlain, again a half decent match, and the uncertainties below that. And I want to show you one example now from the published work already, which is the Facies inversion workflow. We don't have time here to show all the slides, but just a key one here perhaps. And we actually compared two methods, one using the inversion with the Facies-driven trends, and one's with just a constant trend, but structurally compliant. And our measures that we used in this slide are precision, which is the number of true positives divided by the sum of the true and false positives. We can do this analysis at wells. And the bottom horizontal axis requires perhaps some explanation. It says probability threshold here, and what that means is that if you see 0.8 for the probability threshold, that means that only winning probabilities 0.8 or greater were counted, and the rest were not counted. And we can then do this analysis then for a whole series of probability thresholds. And the takeaway is that the red line is always above the blue line, so that second pass of inversion with the Facies-driven model of BPVS and P impedance and density provided greater precision in the final results at the wells. An interesting thing is that the low-frequency model from the constant but otherwise structurally compliant model was not bad at the higher probability threshold, so indicating that for these data at least it was very good first look, as long as one stuck to the higher probabilities. Well, my last slide here on the right-hand side, we just looking back at that effective porosity again in a high porosity body we see in 3D space confirmed by wells. And we started off looking at the petrophysical domain and Facies design, where we designed in the petrophysical domain and then checked that out in the elastic domain. And decided on an optimum set of facies to use. I didn't dwell on this very much, but that step also provides 3D prior probabilities for the facies estimation. Another bonus there. Then we did Bayesian facies estimation, mapping our facies away from wells. The inputs to provided inputs to facies-driven modeling in terms of facies probabilities and means and standard deviations. Then finally we did that facies-driven modeling and showed two cases of low-frequency models for rock trace inversions, which we touched on only briefly, and the newer work estimating reservoir properties, and we showed a bunch of those for a whole variety of uses. So that's the end of my talk, and thank you for your attention. I'll be pleased to answer any questions.